Okay. So yes, am going to report on challenges and strategies when introducing children with cerebral palsy to brain-computer interfaces. And I should convince my slide to advance. I need to disclose all sorts of things, mostly that I've got really good funding people, and I'm very happy for them, including Cerebral Palsy Alliance Research Foundation, NIDLR, and NIH have been quite supportive. And I have wonderful collaborators all over the world. So I'd like to thank them. Always good to put these faces up front so that we get them acknowledged nicely. I'm talking about brain-computer interfaces. And while we like to think that brain-computer interfaces will be utter magic and faster than anything we can possibly imagine, so far they're still awfully slow. The basic idea being that we're putting a screen in front of people and we're having them concentrate on one element on the screen. We flash stimuli for that element or for the different elements, and we can pick out which item on the screen the person cares about. So we've essentially created an on-screen keyboard that is operated by where people pay attention. We are working with that on applications for communication, but this again is with a keyboard, and my slide is supposed to advance here. Here we go. That I'm working with the Parenchyromic company. We have NIH funding, and we are developing an eye gaze accessory. Well, no, they have an eye gaze accessory already. We are developing the brain-computer interface accessory. Their devices already ship with touch screen and switches. You can already buy eye gaze. The plan is that you will be able, when we're done, to buy a brain-computer interface input accessory. And I saw the stimuli flashing on their device hardware last week. So we are making good progress to getting that accessory completely integrated with their system. I have a prototype that we can use now, but that's not really the focus of this talk. I've presented here before about our BCI administered vocabulary test, where we were presenting 4 target pictures, having the person pick which picture matches a recorded word. And we did a comparison with people who could take the standard version of the test and people who could take the BCI version of the test, and got this beautiful graphic. So I'd like to show the picture. And of course, when we took this for people without communication and started testing with people who couldn't take the standard test, we had a lot more challenges. We only had 5 of our 27 participants who were able to even calibrate the BCI. And we had done some simplifications and made things easier, simpler, more step-by-step. We had really tried to adapt this to the population who couldn't take the standard test. But what do you do when you have very few people who can actually take it? Well, you analyze what you did have, and you analyze what you could have done differently. So we have analyzed the factors that were affecting BCI use and affecting the challenges. We just had a paper come out in Frontiers in Human Neuroscience, looking at all of the different concepts and challenges of brain-computer interface use for this cognitive assessment. So I'll go through these in some more detail, and there are certainly some of these that we were beating our head against the wall saying, why in the world didn't we realize that that was going to be an issue? So one of the things that we hadn't anticipated as much was that we had cap fit and stability. We were using the gel caps, and despite our nice circumference measurements, sometimes our caps simply did not fit, or sometimes they did fit, but then they caught on headrests, or they were just kind of turned sideways, which when you're using a gel cap, smears all the gel together and essentially makes like one big electrode instead of multiple different locations. So this was a real challenge for our recording. This is also something that we're hoping to get funding. We have a grant pending to address this issue as a more global issue with accessibility for electroencephalogram for people with atypical head shapes. All the advertisements will say that we fit all different head sizes. It means sizes, not shapes. And they fit 95% of the global population, and that's great, but I want to work with the other 5% there. Now, one option is something like this dry electrode headset, which at least has the advantage of having a smooth outer surface here. So when it interacts with a headset, it's not quite as likely to catch, but there are still accessibility issues there. So one of the items in our concept map there, in our Venn diagram, was the headgear choices. Our wet electrodes are, they feel weird, and that's not something that kids with CP necessarily want to experience. The setup is time consuming, and you need to wash the hair and the cap after use. The dry electrodes are faster to set up. You don't have to wash the hair afterward because there's no gel in there. Not that far back, but there's possibly more susceptibility to movement. There is greater concern about if a person overheats or something, and they're just less studied. The lower accuracy has a question mark because on a good day, I get accuracy that's just as good, but I don't trust it as much. It's very new tech. It hasn't been around as long as the gel electrodes, which are very well studied over decades or possibly even a century. Electrode locations are another topic of interest. The dry electrodes there had only 7 electrode locations. That's part of what can make them easier to set up and quicker to set up, is that instead of the 32 that I was using in my gel electrode study, I'm now only setting up 7 locations. But I need to remember that when I'm working with people with cerebral palsy, I'm working with people with atypical neuroanatomy. So the 7 locations that I'm pretty confident are functional when I'm recruiting off the street, I have more questions for people with cerebral palsy. And this is a study that we are have in review, where we're looking at people who are typically developing mild cerebral palsy and then severe cerebral palsy. And we're looking at customizing the locations that we're recording from. And we're seeing dramatic improvements in the calibration accuracy that we can get when using a custom set of locations instead of using that default set. And it's a lot bigger advantage for people with the greater cerebral palsy. And to define my terms, essentially, this is the group the mild CP group is the group who could take the standard version of the vocabulary test, and the severe CP group couldn't. So I don't have any imaging studies on these individuals. That would be lovely to be able to compare to these results, but I don't have those measures. So then we look at the other things that affect use. Situational anxiety was one of the things we saw. We had people who were just freaked out by coming into our office at all, or who didn't at all like having this headset on. So we do lots of modeling, chatting up with people, providing, can we provide a familiar environment? But really, we need to do more gradual introduction. This study, we were still setting up based on only 1 or 2 interactions. And even though we often ended up with everybody wearing a headset to make it the norm, and we were often able to talk people down by chatting or showing pictures of, my daughter riding a horse and things like that, just to establish some rapport. It's still a stressful thing when people want to put something on your head. Another question that we need to do more evaluation of, and we'll see if this actually activates. This is supposed to be an animated GIF showing really rapid flashes, but perhaps the flashes are actually too fast to see. And it's something that, again, we can accommodate, but it becomes more of a question of how do we evaluate whether people can see the stimuli we're trying to present. We can make longer flashes, but perhaps we need really to make different flashes and more interesting flashes. Even on its best day, white flashes of a gray letter on a black background are boring, and they'll put you to sleep pretty much regardless. So one of the things that we found was kind of our biggest driving factor was that if people had been successful with assistive technology before, then they were more likely to be successful with the brain-computer interface. And this is not really the answer we want, because we want our brain-computer interface to be the assistive technology that works for people who can't use other things. So we're going back and looking at, what really is the key factor here. And we come back to this question of choice making. Do people have the concept of making choices? If you've used assistive technology before, then you have demonstrated the ability to make directed choices, to direct your attention to someone else's instruction. And that's not necessarily something that everyone has if they haven't used other technology. But at the moment, our calibration methods that fit the BCI to an individual require people to make directed choice making. So we're like, aha, we have identified a key problem. We'd like to be able to introduce the process more gradually so that the choice making could start with just an expression of personal preference, even an expression of orienting, looking at the most interesting thing around. Even for people who are trying to follow instructions, then we have the problem of how do you model the silent brain activities? When we try to explain things, we try to explain it, we try to model it by speaking, but then you end up with people trying to speak or trying to make some sound, and that's not only not necessary, but counterproductive. But how do you model? Often our instruction is count the flashes, and a lot of people can have math anxiety. Counting is that scary school thing, and counting isn't necessary. It's just the simplest instruction. So we want to look at individualizing instructions and simplifying the whole process. We started creating some graphics and videos to better describe the process, better explain what's going on in a more accessible manner. I now have a graphical assent form that is essentially my own little mega or cartoon version of the assent, and we have a video of instructions that uses slow motion and zooming in and graying out things we want people to ignore. But I didn't want to show you all of that because we're already short on time. But our big challenge is this 20 minutes of calibration time versus a child's attention span. Even our initial study with people who were able to take the standard test, we had 30% of the participants who weren't able to calibrate the BCI, and it was mostly the younger participants who couldn't keep their attention on the task long enough. They were starting to look where we wanted them to, and then they would be looking around the room, looking at the ceiling, looking at the lights. And this was more of a concern and more of a recurring difficulty as we switched to people with more severe cerebral palsy, because they hadn't had that experience of having to finish their homework paper before going out to play at recess. They were looking merely for the most interesting thing around. And the calibrating the BCI is a very important part to customize for each user, because all we're really looking for, we don't need the counting. We need the difference between a target that they're paying attention to and a non-target. But that could look very different for each person. So if there's a whole bunch of apples coming along and then an occasional orange, we need to know what the brain activity looks like for the difference between those apples and oranges. So we need some data where we know what they were paying attention to. But when we look at this concept map, where do we get a hold of it? There's a lot of intersecting things. And we've kind of chosen that calibration as the thing that we can perhaps warp to get, redesign, redo that so that we can get a handle on all of the other pieces and hopefully make it all come up in our favor and in the favor of the people who we want to be able to use our BCI. So we're trying to attack everything at once, to simplify, to provide acclimation, to provide customization. We want to have the ability to customize the electrode locations if we need to. We want to use the quicker setup electrodes as if we can. We want to have introductory videos to show people what to expect and to model the behavior we want. We wanted to have repeated sessions for behavior shaping and acclimation, even if the first sessions are only come into the room and not have a scary interaction. We want to customize things for individual preferences. We want to use favored images or topics, and we want to be able to do calibration without people having to consciously follow directions. So what we're envisioning is something where maybe we take and get rid of this direction that is count the flashes of the item that matches the word, and instead we say, watch the screen, the animals are going to play peekaboo. And we have something like this show up. So the idea is that it should be naturally attention grabbing. It should be more interesting, or at least more interesting than the ceiling and the lights. And we should still be generating the brain activity that the BCI needs to learn, because we have a sequence of events that are common but uninteresting, and then an occasional event that is straightforward and engaging and interesting. So that's kind of the experiences we've had, the challenges we faced, and some of the things that we hope to do about it.